Okay, great. Well, it is 10 after the hour, so let's get started. I'm Lisa Goldberg, co-director of the Consortium for Data Analytics and Risk, and this is our weekly seminar, and it is my extreme pleasure to introduce this week's speaker, Alec Kercheval, who is a mathematician, a professor at Florida State University, a CDAR researcher, and my friend and collaborator of, I'm a little scared to say this, 40 years. There it is. Alec will tell us about the James-Stein estimator for eigenvectors. And so I will turn over the microphone. One more thing, feel free to interrupt. Alec is open to questions midstream. So over to you, Alec.
Thank you, Lisa. Thanks for the invitation. It's really nice to be speaking in the seminar here again, even if it's over Zoom. And this talk is meant to be sort of an introductory talk to this topic, kind of a gentle, what is going on kind of talk, partly a motivating talk. The work itself, the published work, devolves easily into technicalities and computations, although it's not particularly deep, it's technically lengthy. And so you will see like 60-page papers with lots of computations if you try to read the papers. And the other papers that we're reading by other people, especially statisticians, have that feature that they'll say, well, the proof of lemma B is in the supplementary materials because they're embarrassed to put it in the published paper. So we know what that's like. So anyway, not a lot of technicalities, essentially no proofs. I hope to help with some of the intuition and some of the motivation and what is it that's actually what's the goal and what are some of the possible conclusions. This is all work that's been done in various combinations between me and these other three people, Lisa, Hubeyb, and Alex. Lisa Hubeyb is here in the audience, postdoc here at CDAR. Alex at UC Santa Barbara was a previous postdoc at CDAR. And Lisa and Alex have been working on this question for longer, but I got interested in it when Alex visited us in early 2019, I think. And then I was there in Berkeley for a few months during my sabbatical, and we worked on it more. So I'm kind of reporting the ideas of all of these people in a way. And let me start here. This is not the way that we at first envisioned the project, but this is how we're thinking of it now. And I need to explain why the words James-Stein are in the title. This is Charles Stein, a Stanford mathematician or statistician, brilliant work, very influential. James was his PhD student who was the co-author on the main paper that we refer to. And I want to just describe this work of his from the late 50s, early 60s a little bit as a motivation. And I think it's cool enough that everybody should be exposed to this a little bit. I had never really heard of it before 2019. Maybe statisticians know it better. Here's the idea of it. What you see on that top horizontal line is the batting average for a bunch of different baseball players during some season in the early 70s for the first 45 games of the season. The whole season is 162 games. So you let 45 games go by, they've all been at bat a bunch, and you can look at their batting average. Now, what you are imagining is what's going to happen in the rest of the season. And each of these guys, you could suppose, has an intrinsic hit probability attached to them. And so their 45 game average is just sort of an estimator of that. Was there a question? So like you can see the guy on the right, Roberto Clemente, he's got a 45 game average of about 400, which is pretty good. If you wanted to estimate what his intrinsic hit probability is, given just the observations for the first 45 games, the best you could do is to use this number 400 as the estimator. And the same thing for any of the individual other batters. But if you want to estimate all of them in a way that keeps the mean squared error amongst all the estimates low, you should not do that for the following reason. The guys at the top of this list are going to be benefiting from the random estimation error, which for each guy is symmetric about their intrinsic probability. But for some guys it's going to be a plus, and some guys it'll be a minus. And so odds are that the people in the top half of the list are benefiting from that error, and the people in the bottom half of the list are being detracted from the error. And so to correct that estimation error across the whole population, what you should do is shrink everybody a little bit towards the center, towards the average of all the averages. So this is sort of intuitive, but sometimes, on the other hand, it's called a paradox, because the mathematics of this actually depends not at all on the fact that all these guys were baseball players in the same league. These numbers could have been rainfall amounts in Seattle, price of wine in France, expected mass of a mouse, man, blue whale, an asteroid. And the same theorem is true. Nick, yes?
Yeah, I mean, one way of thinking about it that I'm still not sure is correct is that when you look at Clementi, you think you're seeing a sample of his batting average, but you're really seeing the maximum of 14 or whatever it is batting averages. And so you think, and this is why it's not really a paradox, the sense of paradox comes because you think you're making an estimate of a standalone series, where of course the sample mean would be perfectly fine. But instead, you're actually getting the maximum of a group, a panel of series. And one way to correct for that would be to estimate it as though it were a maximum. And that would lead to a different estimator. I haven't seen work on that, but that doesn't mean much because I'm not as conversant with the literature as I surely should be. But how much content, do you have a sense of how much those remarks sufficiently distill the content, and the extent to which there's a orthogonal observation that goes beyond simply the fact that the paradox consists of mistaking a maximum for a standalone estimate?
Well, I don't know. I don't have a good, clear answer to that, except that the explanation for why it seems paradoxical maybe go beyond that. For example, if you just forget about half of these batters, then you have a different maximum problem. And so I guess we're not used to thinking about people in the context of a group. You change the group, you don't change the individual you're interested in, and the answer changes. That's kind of what's rubbing us raw.
Thank you.
So, well, it is true that this is sometimes called the James-Stein paradox, but you can, if you think about it a while, it doesn't seem so paradoxical, but it is interesting. And this is the more mathematical presentation of that picture with some notation so that I can draw your attention to some formulas. So the mu i's, those are the intrinsic hit probabilities for P players. And then the Z i's, these are the only things we actually observe. They are the batting averages for the first 45 games. Do you guys see my mouse pointer moving? You do? Okay, so that's helpful. I can point with it. So the typical setup for this situation is that you imagine that the intrinsic probabilities are arrayed in a vector of dimension P, and this parameter tau measures the spread of the true probabilities across the population, and their grand mean is this number M. and 1 is just the vector of all ones. So how does the vector the entries of the vector vary from the vector where everybody's average would be constant? Whereas over here, this is the conditional distribution of the observed averages, and the nu squared is quite a different number. This represents the kind of measurement error around the true value that you are observing. So tau represents some characteristic of the truth, whereas the nu has to do with the estimation error. And so you can just calculate, using Bayes' rule, the conditional distribution of mu given z, and its expectation is given by a formula that looks like this. It's just a convex combination between z and the vector of all m's, the constant vector, where you have a constant that looks like this, 1 minus nu squared over tau squared plus nu squared. And the estimator is elementary, with algebra, but it's in terms of unobserved parameters. The m, the tau, the nu are not observed. All we are observing are the zi's, the averages. So we can't use it as an estimator. We need an empirical Bayes estimator, some version of this that has empirical parameters. And we can get empirical parameters. Like instead of the m, which we don't observe, we can calculate the arithmetic average of all the entries of the z vector. And that has the right expectation, so we just use that. And instead of this ratio, nu squared over tau squared plus nu squared, we can look at this ratio, which has the correct expectation. And this s squared is a purely empirical quantity that we can calculate that measures the variation among elements of the z's. And the only thing we don't have in this theory is a way to estimate the nu squared. Statisticians will sometimes say, oh, I'll just set that equal to 1, or find some other independent way to estimate it. So the formulas are always in terms of this sort of hanging parameter nu squared. Okay, so if you take that Bayes estimator for the expectation and you swap in these empirical approximations to those parameters, you get this formula. And this is the James-Stein shrinkage estimator formula from 1961 that became so famous. It's called shrinkage because you're shrinking the z vector towards a vector of constant entries, just like in the picture. And there's a specific amount of shrinkage that you're supposed to use. And you might say, well, we've swapped out the real answer with some empirical versions. Maybe we've lost our conclusion. Well, no, if you use the empirical version, you dominate just using the averages themselves in terms of total mean squared error in expectation for all possible values of the truth and all values of the new parameter. It's more interesting because it works when p is bigger than 3. When p is 1 or 2, you should just use the z estimator by itself. Okay. So this is just a little intro to this James-Stein estimator, which I think is really interesting. It's got, nothing obvious to do with finance, but there's a whole bunch of literature flowing from this. And there's books on shrinkage estimators of different kinds. It really spawned a lot of stuff. So the statisticians know about it, but I didn't. So I like to start off with this. And you'll see why I'm starting off with this in a second. But now I want to turn to financial problems of portfolio risk and portfolio estimation. Are there any questions? Probably not yet. So here's a picture of the efficient frontier that everybody should know. I could make it a little quiz question. Why is this picture incorrect? You can pause the video for a moment to ponder that. It's not actually correct because the efficient frontier is in reality a part of a branch of a hyperbola in these coordinates, whose center is on the y-axis there, even with the green dot. And this orange curve isn't asymptotic to any line through that center. Often people draw it like a parabola, but it's a hyperbola, but it has this general characteristic. And what it is that on the orange line, you have portfolios, the risk and the expected return of portfolios, which minimize risk for a fixed expected return, expected excess return. And those are important for portfolio construction, obviously. This is a Markowitz theory. And all of those portfolios amount to solving some kind of problem that looks like this. This is maybe the prototype problem. Minimize the variance. The W is the vector of portfolio weights. And the sigma is the covariance matrix amongst all of the returns of the assets. So W transpose sigma W is the variance of the return to the portfolio W. Want to minimize that subject to some constraint, like the fully invested constraint that sits here. You can also add other constraints and get similar theory. There's work in progress by some of us on that, and so forth. We'll talk about more different possibilities later, but to get the ideas, let's zoom in on this particular problem, minimum risk. So this is trying to identify the portfolio that's there in the green dot in this picture. It's an easy problem if you know what sigma is. You just can write down the answer using calculus. Lagrange multipliers, an exercise, simple formula. Problem is we don't know what sigma is. So we have to estimate sigma. And if we estimate sigma, then we get some estimated W. And the question is, how much of a whipping do we have to accept in order to get that estimated W? Here's one of the problems. If the estimated covariance matrix has some error in it, as it will, then when you minimize the risk using that noisy estimate of the covariance matrix, what's going to happen is that securities for which the variances are underweighted or correlations that are under forecast are going to be overweighted in the portfolio. And so there's a bias for a total under forecast of the portfolio variance, even if there's no bias in the noise that appears in the covariance matrix. This is a problem that's being generated by the optimization process of getting to the portfolio. That is a bad kind of error for a portfolio manager. Of course, you don't want to have less risk than you think. You'd rather have the opposite error, but this is the bad one. So we have to address it. And how do we address it in mathematical finance? What we're going to do to try to figure out where it's coming from and how to reduce the error and therefore get better optimized portfolios, which is a quick way of saying the general agenda of the overall project, is we're going to use a factor model. We're going to use a factor model to make it easier to estimate risk, which, that is a standard idea now, but let's look specifically at how the error is propagated into the portfolio in a factor model. And the easiest thing to do would be to start with a one factor model, which I've written here, R equals beta x plus epsilon. R is the return. That's the only thing we observe, excess returns. That's a vector. So I'm in dimension P, maybe P equals 500. And I'm looking at returns, which I'm presuming represent the output of a model like this. Beta is the p-dimensional vector of the stock betas. X is a scalar random variable that represents, say, the market return or the return on this beta factor. And then epsilon is a vector of the specific returns. That's a random vector. Epsilon is not noise. That's kind of where we part company from the statisticians. What they often are trying to do is estimate this beta x part, thinking of epsilon as Gaussian noise or something. we've got this model where the epsilon is part of the signal we're interested in. But in this factor model framework, we always are going to assume that the epsilon is uncorrelated with the x. Beta is a fixed vector of parameters that we'd like to estimate. X is a random variable. Mean 0, epsilon has mean 0, and we're going to just assume that the variance of x is some parameter sigma squared that we also don't observe. And it's convenient to assume that all of the specific returns are uncorrelated with each other and all have the same variance delta squared. So that leads us to this equation in the center here, sigma equals sigma squared beta beta transpose pros plus delta squared times the identity matrix. That is the true or population covariance matrix for the returns generated from the model at the top. And so this is sometimes called a latent model because we don't observe anything except the output. Notice how if we doubled beta and cut x in half, we'd never know. So we can't actually estimate the magnitudes of beta or x. We can only estimate their product. So it's convenient to just combine those two magnitudes into a single parameter and get this expression at the bottom for the covariance matrix. You can see now the estimation problem is reduced to estimating three things. We've got two scalar parameters, an eta squared and a delta squared, and then a vector. This is now a unit vector, B, which is the leading eigenvector of this matrix. It's a positive definite matrix with leading eigenvector B, leading eigenvalue eta squared plus delta squared. We like to estimate that. So we're living in the world where we've got this factor structure and we have to estimate these parameters. Okay. All right, well, here's an estimate. Some eta hat, some B hat, some delta hat. And we got to figure out how to get those things. So now here's our context that we're worried about. We're not in the classical statistical context where we have a long time series in small dimension. It's the opposite. We've got a time series of a fairly moderate size of observations n in order to estimate a p by p covariance matrix in dimension p, where p is rather large. P is 500 or 3,000 or more, and may be rather small. If I'm doing monthly observations, n is probably only 24 or something, because I don't want to look farther back than a couple of years if I expect any of the data to be relevant to a future risk forecast. If I'm going to use daily or high frequency data, I have to start worrying about serial correlation in my observations. And so, which means I'm going to have to try to filter them somehow first, which brings in an extra layer. And so I'm often constrained on the length of time series that I'm able to have. So this is our framework here. It's large dimension and fairly low number of observations, low sample size. And in that context, we can take the observations and we can form a sample covariance matrix, which is going to be rank deficient. It's going to have rank at most n. So it won't be a candidate for the covariance matrix in an optimization problem, because we just get 0 if there's 0 eigenvalues. So we need something of this form, sigma hat, that we have here. So the principal component analysis would look at S and just extract its leading eigenvector. And that would be a good starting candidate for the leading eigenvector B hat here. And it's not hard to also get estimates for the other scalars. I don't want to talk about that though, because I want to focus on the eigenvector part. Nick, yeah.
Yeah, so leading, of course, means biggest.
According to the biggest eigenvalue.
And according to the biggest eigenvalue, and that means we're looking for Clementi again. And that the errors in estimation are going to lead to a eigenvalue that's bigger than it should be, because we're looking at the biggest. And it's going to have some coordinates along the axes that are bigger than they should be, because the sample error is going to produce some of our many axes. We have a lot of axes, and some of them are just going to have components of this eigenvector. They're simply too big, and others are going to be too small. So we're going to get a list of coordinates along the p-axes that are really spread out in the same way that Clementi's average is just too big relative to what it should be. Did I get that right?
I think the analogy is pretty good. The Clementi kind of represents the largest entry in the vector B. It's not that Clementi was the leading eigenvector. He's just a large entry in a vector.
So can I interrupt for a second?
Yeah.
I agree that Alec, Nick, I don't think it's a perfect analogy. So let's separate two things, the eigenvalues and the eigenvectors. And there's a darned big theory of the spectrum of eigenvalues. And in that case, too, the biggest thing is too big and the smallest thing is too small. There's some theme going on here. When you estimate a bunch of stuff, some way or other, the biggest thing is too big and the smallest thing is too small under some conditions. But what Alec said, I completely agree with. We're not interested in that eigenvalue at all. In fact, miraculously, in a lot of situations we care about, the error in that thing, just while it's there and it is have a sign that you expect, probably it goes away. And so this is the analogy is not the vector is Clementi. The analogy is the vector is the whole list of baseball players.
Right, but it seems to me the problem replicates itself because we're looking on this huge sphere relative to n, this very, very big sphere, and we're going to find out where something's maximized, and it's noisy. So that place is going to, for all the reasons that you've alluded to earlier, Alex, is going to reflect the maximum error along certain securities, i.e. along certain axes. And that is going to have a similar effect on the coordinates of the eigenvector along our given axes. We don't, I mean, with PCA, we're trying to find new axes, but we're given a set of axes by the framework of the problem. And some of those coordinates, I think by analogy, are also going to be like Clementi. I guess there's no more content than that. So I rest my, I withdraw my question.
Well, I find that explanation to be more intuitive explanation for the fact that the eigenvalues of the sample covariance matrix are overly dispersed. The highest eigenvalue is too high. The lowest eigenvalues are 0, so they're too low. That's happening at that level. Thinking about the vectors, maybe you're right in terms of thinking about the coordinates, but it seems a little less immediate that will be happening there. But effectively it is. So we're only talking about what's a like intuitive explanation for the truth here.
Can I just comment quickly? The smallest eigenvalues are indeed 0, but they're not too small. They're right, because if it's the dimension of the matrix, if n is bigger than t, then there are n minus t eigenvalues, which really are 0 in the population, and also which are estimated as 0. But the smallest non-zero eigenvalue is too small.
Yeah, so the 0 eigenvalues in S must be there. But in the population covariance matrix, the smallest eigenvalue is delta squared, not zero.
I'm sorry, you're right. Yeah, you're right. I'm sorry, I got it wrong. You're right.
Yeah, but there are other situations also where the number of observations might be a little bit bigger than the number of variables, and then you don't get,
Yeah.
the big case actually that people care about. But there's a lot of directions to keep track of here.
Yeah. So let's try to focus on just a few things here. So Lisa just said that eigenvalue errors actually have no impact on the error in the estimated variance asymptotically, which was early on sort of a surprise. The variance error that you make in constructing this minimum variance portfolio is dominated by error in the leading eigenvector. You can write down asymptotic formulas. The true eigenvalue appears, but the estimated eigenvalue only appears in the terms higher order in 1 over p. So for large p, there's no benefit to trying to correct the eigenvalue if you're trying to reduce error. I'll show some experiments later. So this kind of justifies why we're focused on the eigenvector, which is a harder thing to study. For one reason it's harder is that it's hard to understand what an eigenvector is. Paradoxically, it's really not a vector. It's a direction. It doesn't have a scale, and it doesn't have a sign. And so we're all used to using vectors to analyze everything, but it's helpful to try to think in the category of directions when you're thinking of eigenvectors. So this is sort of a hidden difference between the James-Stein theory and the James-Stein for eigenvectors theory, because the eigenvector theory really takes place on some perhaps projective space or Grossman space or something that's not really a Euclidean space intrinsically, although we're not trying to grapple with that yet in our statements, but it has an impact in how we think about it. So we've got an analog of James-Stein, which we're calling JSE, James-Stein for eigenvectors. And it's similar to the James-Stein. It improves on the PCA leading eigenvector as a estimator for that B vector in the population covariance matrix. And here it is. I'm showing you, remember, S is the sample covariance matrix from the data. H is the leading eigenvector of S. Lambda squared is its leading eigenvalue. In black here, I've rewritten the James-Stein formulas. And now in blue, these are the JSE formulas. And I put them together so you can see that they're almost the same formulas. And this is basically the reason why we're calling it what we're calling it. Same formulas, except the variation term, we're using lambda times H. H is a unit vector, so that's sort of a scaled eigenvector here. There's a P instead of a P minus 3, but our results are asymptotic, so that's no difference. And we have a bonus here that we actually do have an estimator for this new squared part. It's given by this expression, which is equal to the average of the non-zero eigenvalues below the top eigenvalue for S, scaled by 1 over P. And that's the number that converges to delta squared over N. Remember, in our asymptotic regime, we're imagining that our N is actually fixed, but we're going to let P go to infinity. So this gives an empirical definition. We can calculate this just from the observed sample covariance matrix, which is calculated just from the observed returns. And what's the point? Well, in order to state a theorem, I have to tell you what we're going to measure, what the metric is for success. So here's a couple things. One of them is just squared tracking error between the estimated portfolio and the truth. It's a familiar object, I hope. Another one is this variance forecast ratio. So I take the variance that I think I have with the estimated portfolio and divide it by the actual variance it has that I can't calculate because I don't know the sigma. But in theory or in simulation, I know what that is. And I want this variance forecast ratio to be close to 1, but it may well be much less than 1 if my risk I think I have is much smaller than the truth. So this is something I'd like to look closely at as a measure of error in estimation of risk for my portfolio. And then before showing the results, I want to set up 3 possible estimators for the covariance matrix to compare. And you don't have to look carefully at these formulas, but let me just describe what they are. For the raw estimator, I'm just going to use the PCA leading eigenvector for my estimator of little b. And these numbers just mean that the leading eigenvalue of this matrix is equal to lambda squared, the leading eigenvalue of S. We know that is going to be too high, biased upwards, but we just plug that in. That's called raw. For the PCA estimator, let's just correct that eigenvalue. So now this formula gives me what turns out to be an asymptotically correct eigenvalue. It'll converge in the limit to the true eigenvalue of the population covariance matrix. But I'm still using the PCA eigenvector there. And I've already said that it's that eigenvector that's really the most important thing. So I haven't corrected that yet. And finally, the JSE estimator is where I put in this JSE eigenvector correction that I had on the previous slide. And the little bar over the top means I'm just normalizing it to a unit vector. And then I can use each of these covariances to produce a portfolio, an optimal portfolio using that covariance matrix, fully invested minimum risk portfolio. So there's the theorem. This is sort of like the analog of the James-Stein conclusion, only instead of an expectation, the conclusion here is almost surely asymptotically as p goes to infinity. And by the way, p for realistic values of p like 500 and 3000 in simulation, we already see this asymptotic effect happening. So it's not like p has to be 10 to the 23rd. P can be very moderate, and we'll see this. But the theorems are proved in the asymptotic regime. Also, the variance forecast ratio for PCA tends to 0, which is terrible, but stays bounded above 0 for JSE. And experiments suggest that actually it tends to 1, but we can't prove that yet. And the tracking error is dominated with the JSE estimator. And these are all almost sure conclusions asymptotically. Now, a lot of the statistical literature has conclusions and expectation or distributional conclusions. So this is a pointwise almost sure conclusion. And it's because we don't have hypotheses about the distributions. So if all the statistical papers I'm reading, they say everything is Gaussian, and then they try to calculate with Gaussian formulas. Whereas here, the technique is to use the law of large numbers, different versions of the law of large numbers, which is insensitive to the choice of parametric probability distribution. The only thing we need are some mild moment bounds on the distribution, and then all this stuff is going to work. So in particular, we can have student T or fat-tailed specific returns distributions, no problem, everything still works fine, including in simulation. So I want to sort of finish this by showing you some experiments, some simulation experiment results. But before that, here's a nice picture that was drawn by Alex Shkolnik. And I think a version of this is in this paper of Lisa, Alex, and the other Alex, just to kind of illustrate some of the geometry. Up here, Z is the North Pole. That's the vector of all ones normalized so that it's a unit vector. And part of the theory predicts that with high probability, the configuration of the PCA vector, the true population eigenvector, and Z look something like this. H is a little farther away. And if this is the configuration, then it makes sense that if you were to kind of shrink H along this geodesic towards Z, which is what the shrinkage formula is accomplishing, then for a while you should be getting closer in distance to the B. You're not correcting this horizontal angle, but you're correcting the dispersion of H in this picture. So as H gets closer to the North Pole, it becomes less dispersed. And at some point in the middle, and there has to be a stopping point that's data driven, you can stop and you can be closer to the B than you were before. But you're supposed to imagine this sphere in very high dimensions, which is not a very helpful comment. But just want to say, Z is the vector of all ones, but actually, there's nothing special about that vector. And so you can do the whole theory at another base point. And so here, I don't necessarily want to absorb these formulas, but just to show you that there are analogous formulas, if you like, where you replace the North Pole with another base point of reference. The idea of the North Pole was that it was relevant to our problem because that North Pole was in the constraint in the optimization problem. But you might have other problems with other constraints, in which case you can make other estimators where you shrink in different directions and you get the same results. So maybe I'm not going to focus too much on the details here, except just to make that comment. We're still trying to figure out the best way to say this stuff. But this is just a way of saying the theorem. This is going to appear in probably not exactly this version in the paper that we're working on and keep revising. And that is that similar quality results if you use a different base point asymptotically. There's a hypothesis here, which is that B and the base point tau should not be at right angles to each other, or else you don't get any improvement. So that's why this assumption is down here. Okay. Here's a famous to me picture that Lisa drew when we were looking at trying to understand why our referees didn't understand what we were saying. And the reason was we didn't really realize that they are all always naturally thinking about this HH regime where both P and N are going to infinity. And we're doing a very importantly different thing. We're calling it the HL regime. We didn't invent this. People have been working on this area for a while, but not applied to this problem, where P is going to infinity and N is staying fixed. It's related to the classical statistics situation where P is fixed and N is going to infinity, but it's not equivalent to it because if you take an IID series of observations and you interchange N and P, they're not IID anymore. There's correlations across the P direction. But you can overcome that and basically do strong large numbers along the P direction to get these results. So this is like a less studied, interesting area that we're trying to attract some more attention to. So here's a few experimental outcomes. We're just simulating with representative parameters from the market, essentially. This is 252 days of IID simulations using this model. And just to illustrate, here this GPS refers to the JSE choice of estimator. So we do the whole problem with the PCA estimator, where we use the leading eigenvector and look at the tracking error, 100 different simulations. So this box plot is kind of summarizing the distribution of tracking error outcomes across 100 independent experiments. And you can sort of see that things get better when you use the JSE estimator, and they also decline fairly rapidly with the dimension of the problem. This represents the number of assets in the problem, which is sort of what we are expecting. Our asymptotic results should show, good results asymptotically, and then we're sort of seeing the asymptotic effect coming in here. It's rather mild up here, not much is happening. Here's a picture of the variance forecast ratio. This is even more dramatic. Not very good results here. We know theoretically that the variance forecast ratio is tending to 0 asymptotically if you use the PCA eigenvector, which is very bad. And we know theoretically that the JSE variance forecast ratio remains bounded asymptotically, but in fact, it's converging to 1. So if we could just figure out how to be smart enough, we'll be able to prove that. So it's, from this point of view, if you're interested in variance forecast ratio, it's a tremendous win. Not sure if we deserved a tremendous win, but there it is. I mean, I think this was one of the big drivers in the early work that was being done by Lisa and Alex.
Is that the variance forecast ratio for the Minvera portfolio?
Yes.
And is it long only or long short?
Long short. We don't have any inequality constraints in this problem.
Yep, thank you.
Yeah, sure. Here is an experiment with the tracking error. You can see we have a better artist now. And these are the 3 covariance matrices that I told you. The raw one is with the naive choice of eigenvalue. And when you correct the eigenvalue to get the red one, you don't see much improvement, or really any improvement. But finally, when you correct the eigenvector, then the tracking error improves. So we shouldn't spend any time trying to correct the eigenvalue. Of course, the eigenvalue will influence your point estimate of the variance. It's just that it's not influencing your error. Another one on variance forecast ratio, same story. Correct the eigenvalue, not helping, but correct the eigenvector, now we're talking. Okay, that's the experiments. So a lot of things are happening right now, trying to figure all this out more and better. We're figuring it out kind of better and better. Actively revising papers is basically what's happening amongst the collaborators. So some of the things, Alex and Hubeyb are going to be sharing with us pretty soon, I think, a version of this with multi-factor models. Instead of just a single factor with beta x, we would like a finite number of factors. And I think similar conclusions, but there's technicalities. Other group of us working on when you have multiple linear constraints. We would like to see figure out how to do experiments with empirical data, but there has to be some filtering. So we've just gotten so enamored with the theoretical problems that we don't have. I have a few students here that I'm trying to get to do some empirical experiments using actual prices. And then if we wanted to talk to the statisticians more, it would be nice if we could analyze what is going on here in finite p and in expectation. And then I think those guys would be more comfortable because it's what they're used to thinking. And I can't tell how close we are to that. Because the formulas are the same, that's kind of a hint that there's going to be statements like this. But I can't tell how close we are. So there's a few different things that are on our radar. And these are the heroes that I've mentioned. And you don't have to write these down, but there's a few papers that we're talking about. This last one is no longer forthcoming. That's now been published. And this is one of those bad papers I was talking to you about where it says, please see the supplementary material for 30 more pages of calculations. What got me started on this was this second paper, which it's published in 2022, but there were drafts 4 years before that or something. And so I spent a lot of my time in Berkeley in 2019 with this paper. So that's been the inspiration for everything that I've been working on. And then I was lucky enough to have Hubeyb with me here in Tallahassee, and we worked pretty hard. And his dissertation involved this paper and some other stuff. And so now we're hoping we're all going to continue. This is the Markowitz paper that we have to bow to. This is another paper by Alex here that's also in the same direction. He's broadening out his scope a little bit. And it's only here because my bibliography program puts everything alphabetically, or I would have put it above Markowitz. So anyway, that's it. Thank you so much. You've been very patient. You've been a great audience. Happy to answer any more questions.
Well, Alec, you're a great speaker, but I want to make a response to something Bob asked before letting always try and go first here. If you were to do a long only portfolio, you would want to shrink it optimally in a slightly different direction, taught to you by which are the binding long only constraints. And because that direction is not going to be probably as close to the leading eigenvector as the all ones, the best improvement is going to be lower quality, but there still is a best direction, and it still will improve things as much as it can within this kind of theory. And that was pointed to by Alec's generalization, where he said change base points, but you can also have a fatter base point, which is a subspace of dimension k, where k is the number of binding constraints that you care about in your problem. Just project in that direction instead of in the direction of a point. And pretty much all the machinery just walks through to that case. We learned about this fairly recently. I'm trying to write it down. Did I get that right, Alec, or is it a complete overreach?
That sounds good to me.
Yeah. So if you're long only minimum variance portfolios are certainly more useful from a practical standpoint than long short ones, but the long short one is super instructive. So it has taught us many things. I'm grateful to it. So now that I've done all that talking, do we have any questions or comments from the audience besides me?
I have a question. Can you hear me?
Yeah.
Okay,
Totally.
good. Yes. So as a practitioner, I mean, I've evaluated this paper and I told Lisa this is really great, practically speaking. But I'm a long short investor, and so it really works in long short space to the advantage of the portfolio. I was wondering if Alec, you have looked at what consequences you might have in the loan only portfolio. Is there some observations that you made that might be, relevant to this analysis?
I think that's a super important question. And I just have not spent any time on it because I've just been hard enough to figure out the long short theory. And so I don't know anything more than what Lisa just said.
Okay. Yeah, I was just curious because I know that the shrinkage works really well, especially in volatile markets. That's very important to implement. In long short world only, I would be curious to see what happens in the long only world with the same analysis. Yeah. Maybe there's a paper.
Yeah, no, I'm sure it is.
Thank you.
Thanks.
Yeah, so Julia, I have a question for you. Like I was saying, if you do a long only portfolio, you're basically adding a lot of inequality constraints, one for every security. So if you got 3,000 securities, you got the 3,000 constraints, and they're not all binding. So the question is, can we make a good guess ahead of time, the two of us say, at which directions are going to be binding? And if we can do that, we can do this shrinkage problem. We wouldn't shrink toward by lowering dispersion, we would shrink in the direction taught to us by those with the binding long only constraints.
Right,
This
but my question would be like whether the binding constraint is more important than the shrinkage, because practically speaking, in most of the portfolios, you will have a skewed distribution of betas between the long and short side. And I was just wondering, like, because it will be different effect of the same shrinkage parameter on two different sides. So you typically have very high betas on the short side and very low beta on the long side. And I can't really picture myself in my head, like looking at that previous diagram, whether there's any asymmetry and whether the like long only constraint might particularly dominate the portfolio construction, even if you trying to do the shrinkage, whether this will actually add any value or the constraint will kick in first.
Yeah, so if we were to do that problem, the optimization knows that when you try to minimize variance, you want to go short high beta stocks and long low beta. It knows that. And then when you tell it, here is the boundary, so actually now I'm kind of thinking out loud, I think we can answer this. We can guess pretty well at which securities the optimizer is going to want to try go short, and we would use that information to modify the shrinkage direction. Could you put up that picture, the one that Alex drew? So the way we would use that information would be to take this picture right here, and we would pick a different, the B is the same and the H is actually the same, but we would take a different Z. And the information in those binding constraints, which are the ones on the high beta securities, would tell us how to move Z. And would move, and then we would do a different direction shrinkage that would be optimal for that problem.
I see. And so that's right. You solve for Z kind of first.
We solve for Z out of the constraints, shrink in a different, and we know how to do that now, although I won't be able to send you a paper that explains how to do it until Hubeyb tells me it's written down properly. But we know how to do this now. And basically you take the subspace where the subspace determined by all of those long only constraints and project B onto it. That's your direction.
I see.
And you want to shrink. You want to shrink toward that subspace with all the, sorry, what I said was wrong. You want to take the subspace with all those constraints on it and the fully investment constraint and just shrink in that direction.
Yeah, I can see what you're saying. Yes.
Yeah. So so now the information combines, because the information about who I'm going to go short, you just reminded me, it's the high beta stocks, tells it's all encoded in there. Now, because the shrinkage works really well when Z and B are close. And when we get the new Z, it's probably going to be farther away from B than this shrinkage. So it's not going to work as well, but it'll work as well as it can in that problem. And that goes back to this old intuition of Ravi Jagannathan and Ma, which says that the long only problem kind of diminishes the amount of shrinkage that you need to do to get to the right answer, and that is going to be rediscovered, that point, in a completely new framing with this setup. But the answer is, yeah, you can totally do it.
Right.
It's taken 5.5. We started with a long only problem, and it's taken me 5.5 years to begin to see how to do it. But I think I see the path now. And it just completely lines up with pre-existing theory.
Great, thank you.
So more questions? Going once. Well, thank you, Alec, for a magnificent, clear, insightful talk, extending what we know. That was great. And next week, for something completely different, CDAR researcher and co-founder, actually, Jeff Bond, is going to be talking in person at Cal. So please come out to Cal if you're not in Tallahassee. Well, you're welcome to come if you're in Tallahassee, but for those of you in the Bay Area, please join us on campus for an in-person talk. It's great to get together now that we can do that again, not on Zoom, although Zoom's great too. So between now and next week, have a great time. And Alec, thank you again. It was awesome.
Thanks a lot. Nice to see everybody.